Today we're talking about Chapter 11, Section 4, the fundamentals of probability. Now, this is a pretty simple section, and probability will get a little bit tougher in the next section. But for this one, I feel like I'm teaching a lot of courses this semester. I guess it's just in another class we talked about probability, but I don't know, or we haven't this class. I don't remember. Maybe we're just getting more in depth. All right, so what we're seeing here is we're seeing a lot of math jargon, a lot of notation, variables, things like that. But if we break it down, go over it is pretty simple. So we're going to talk about flipping a coin, right? Of course, that's always the probability test is flipping a coin. So we're going to toss a coin, and we know that it is likely that it's either going to land heads up, or tails up. So we're going to denote heads as H and tails as T. All right, the actual outcome is uncertain, even though there's equal chances of both of those happening. So any occurrence for which the outcome is uncertain is called an experiment. So tossing a coin is an example of an experiment. The set of all possible outcomes of an experiment is the sample space. So the sample space of flipping a coin, right? S is denoting the space, the sample space. Your possible outcomes are heads or tails. Pretty easy. So an event, which we're going to call E, is a subset of the sample space. So for example, the subset E, again the event, equals to T. All right, that is the event landing on tails when the coin is tossed. So theoretical probability applies to situations like this, in which a sample space only contains equally likely outcomes, all of which are known. Where we know the outcomes, we don't know what they will be, but we know what the outcomes can be. So to calculate the theoretical probability of an event, we divide the number of outcomes resulting in the event by the total number of outcomes in the sample space. So all this, like I said, looks like complex math jargon, but we'll see in the examples it's pretty darn easy if you can just think about this logically. So let's go and look at this. So the probability of an event is equal to the number of outcomes in the event divided by the total possible outcomes uh, of the sample space. Okay, so for instance, if we were to look at this flipping coin heads or tails, just looking at this particular formula wrapped up into this one. All right, so the probability of E is equal to the number of outcomes that result in tails up, right? And again, this says number of outcomes in event E. So how many times can tails, or the number of outcomes that result in tails up? Well, it's just one, and then divided by the total possible outcomes, which is 2. And of course, we see all we're doing is just following along with this formula. But again, this formula is the formula that you know of. You've known this formula your entire life, not just flipping a coin, but like passer rating or something, right? Quarterback stuff, football, basketball, free throws. And so you've known about this. You just might not look like this. All right, so let's go ahead and look at an example. Alrighty, so a die is rolled. Find the probability of rolling. Okay, so looking at A. Alright, well, first of all, let's just go ahead and figure out how many possible outcomes there are in our sample space. Okay, so let's actually do that before we begin. And again, this is probably super duper redundant because I mean, there's 6 sides to a die, but just to follow along with our formula per se, I guess. We're just going to write down our sample space. So our sample space of our die is going to be equal to, okay, well, what are the possible outcomes of rolling a die? All right, well, the possible outcomes are 1, 2, 3, 4, 5, and 6. Those are the possible outcomes. Okay, well, with that said, we also we know that we have 6 total outcomes. So the number of outcomes here is just going to be equal to 6. Right? So again, that's kind of redundant, but we're going to write it anyways, and then we can proceed with this problem. So A, look up here. A, find the probability of rolling a 3. Okay, well, how many 3 are on a die? Well, there's only one, right? So there's only one 3, and there are 6 sides. So the probability there is going to be 1 over 6. And that's it. Let's look at B. An even number. Okay, so how many even numbers do we have? We have 2, 4, 6. All right, so we have 3 even numbers out of 6 possible numbers. So that's just going to be 3 divided by 6, or 1/2. All right, a number less than 5. Alrighty, so the number it's saying that it is strictly less than 5. So if a number is strictly less than 5, how many of these are less than 5? Well, we have 1, 2, 3, 4. There are 4 numbers that are less than 5. So you would just simply do, again, 4 divided by the sample space, 4/6, or 2/3. D, a number less than 10. Okay, well, looking at this, every single number is less than 10, right? So it would just simply be 6 over 6, or 1. Let me see, and then the E. Okay. So a number that is greater than 6, again, we're looking for a number that is strictly greater than 6, and we only go up to 6. So we would say, okay, there are 0 numbers that are greater than 6, but there are 6 possible outcomes. So my probability there is 0. Alrighty, so what's that? Maybe it was odds that we talked about in here. I forget. Alrighty, so this next example we're going to be dealing with a deck of cards, and you probably are pretty familiar with a deck of cards, but in case you're not an avid poker player or something, we're going to go ahead and just go over them real quickly. So in a standard 52 card deck, minus the jokers, we have 13 of every suit, ranging from ace all the way to king, and of course we go numerical all the way up to 10. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then from there we have Jack, Queen, King. So we've got 4 suits, and of those 4 suits we have one of each number slash card that I spoke about. And that's really about it. So let's go and look at A. You are dealt one card from a 52 card deck. Find the probability of being dealt a king. Okay, so let's go ahead and denote our sample size. Let's do this real quick. Let's denote our sample size. I'm not going to go ahead and write every single card like I did here with every single side. Instead, I'm just going to write the number of items, the number of elements in my my sample set. Okay, so there are, as we know, there are 52 cards. So we're going to say n of my sample space is 52. Okay, and that's just basically going to be my denominator with every one of these, which by the way, I guess I could have said, but yeah, this number here, as you recall, was my denominator in every single problem because I'm dividing by my sample space. So now let's look at A. All right, so A, what are the odds that I'm dealt a king? Okay, well there's one king of every suit, and there are 4 suits, so there are obviously going to be 4 kings. So I would say 4 kings divided by 52 possible outcomes, or 2 and 26, or 1 in 13. Well, 1 in 13 chance of having a king with that one card being dealt. B, a heart. Okay, so now let's think about this. I said a moment ago that a deck of cards is split up into 4 different suits, split equally among 4 different suits, right? And since there are 52 total cards, if I were to split that into 4 even suits, then I would have 13 hearts. Okay, well, again, all I do is I take that 13 and then I divide it by my sample space, 13 divided by 52, which is, well, it's 13 divided by 52. No, it's 1/4. 1/4, sorry. There we go. Yeah. All right, so there is a 25% chance that the card I'm dealt is going to be um, a heart. And then C, what is the probability that I am dealt a king of hearts? Well, there is only one king of hearts, so it would just simply be 1 over 52, and we cannot reduce that any further. So I guess we can say 0.5 over 104. No, I'm just kidding. All right, and so that's that. Okay. Uh, um, you know, that's funny you say that because to me I just assume everybody did, especially during COVID. I played I played so many card games over COVID. Um, but I mean, you say that, but I mean, a lot of what we are doing in this course um, isn't just the normal abstract math that we're used to. A lot of it does relate to real life. And I mean, if you haven't experienced cards, then that's just that's life. All right, so example three, probabilities and genetics. um, I'm guessing you haven't had too many courses in genetics either. Um, so if I recall, this is just called a Punnett square. I haven't done a Punnett square in decades, but they're pretty easy to navigate if you have the foundation here. So let's go ahead and get this foundation. So reading here, each person carries two genes that are related to the absence or presence of the disease cystic fibrosis. Okay, so each person carries two genes. Most Americans have two normal genes for this trait and are unaffected by cystic fibrosis. However, 1 in 25 Americans carry one normal gene and one defective gene. If we use C to represent a defective gene and C a normal gene, such as a carrier can be designated as capital C, lowercase c. Thus, capital C is a person who neither carries nor has cystic fibrosis. Capital C is a carrier, and lowercase c is going to be someone who is sick with that disease. Of course, we see this shown in the table, so us go ahead and kind of dissect this table so you can really understand what we're doing here. The way the Punnett squares work, and you don't necessarily need to know this to create a Punnett square, but the way this works is you basically just think of it as a box, and let's go ahead and make a box because I think it'd make it a lot easier to visualize. Okay, all you're doing is just basically intersecting them here. So you'll have a capital C, and then you have a capital C. Oops, let's make that blue. Capital C, lowercase c. Again, looking at the intersection here, and then we intersect here. We'll put the capital C first, and then lastly we've got the lowercase c, lowercase c, and that's all the Punnett square is. But anyways, what the Punnett square is used for is probability. I'll be honest with you, I don't think it's abundantly useful, which is probably why I learned it one time. And for the record, I'm 12 credit hours away from a biology degree. So I learned it one time for like 4 minutes, and I've never used it again. And I was going into biology. Now I could be wrong, could be using it more, but whatever. I don't think it's that useful. And of course, I don't know, probably shouldn't have said that. But anyways, let's go ahead and return to the problem before we talk about my opinions anymore. So if each parent carries one cystic fibrosis gene, what is the probability that their child will have cystic fibrosis? Okay, well, if each parent carries one of the genes, okay, and so we have the first parent, which is the capital C lowercase c, the second parent, which is capital C lowercase c, okay, and of course we denoted the capital C lowercase c as a carrier, right, a carrier of cystic fibrosis that does not have cystic fibrosis. Well, if we look at this, and of course creating that Punnett square like we did a moment ago, we know that capital C is not somebody who will have cystic fibrosis. Neither is capital C lowercase c. Okay, there's only one possible outcome here, that where the offspring will have um, lowercase c. So if there is one possible outcome, and if there's one outcome and four possible outcomes, well then it's just going to be 1/4. Okay, the probability that their child will have cystic fibrosis is 1/4. All right, so next up we're going to look at empirical probability. And empirical probability is it sounds a little like a little much, but really it's just data. That's all it is. It's just data. So that's it. Okay, so we'll go back. Alrighty, so empirical probability, theoretical probability is based on a set of equally likely outcomes and the number of elements in the set. By contrast, empirical probability applies to situations in which we observe how frequently the event occurs. Okay, so again, it's just it's values that we know are true by observing it through polls. I don't really know what other else, but that's yeah. Bear with me. So we use the following formula to compute the empirical probability of an event. It is the exact same formula. It's just the words are slightly different, but it's the exact same formula. And so we're going to kind of hand wave through that and actually go to the example so I can show you how it's pretty much the exact same formula. Let's see. All right, this is unfortunate. Oh no. All right. Well, yeah, we'll do that. I don't really like having that great question popping in there, but whatever. Let's actually go and put it in there. Who cares? There. Alrighty, so example 4 reads, in 2015, there are approximately 254 million Americans ages 15 or older. Okay, and again, it's ages 15 or older, it's not all Americans. Alright, so table 3 shows the distribution by marital status and gender of this population. Numbers in the table are expressed in millions. Okay, so this chart actually does a good job of kind of breaking down and adding all the numbers for us, so that's good. But let's just go ahead and familiarize ourselves with this chart. We have male in the first row, female in the second row, and then we have the total down here in the third row. And then the first column we have married, second column never married, third column divorced, fourth column widowed, and then the fifth column total. And keep in mind all these numbers are in millions, so there are 11 million male divorced, and then there are 15 million female divorced, and there are a total of 26 million male and female divorced. Of course, you can say that with all of them. So if we were to solve A, all right, it reads, if one person is randomly selected from the population described in Table 3, find the probability to the nearest hundredth that the person is divorced. Okay, well, what we're going to do is we're going to say, okay, so we're just wanting to find out if they're divorced. Doesn't matter if they're male, doesn't matter if they're female. We just want to know if they're divorced. Okay. Well, looking here, there are 26 million people that are divorced. Okay, so we would say 26 divide by how many people? Well, there are 254 million people, or we're just going to put 254 because we know that all these numbers are in millions. 26 divided by 254, and I haven't had to use there it is, my calculator yet, I didn't know where it was. So it wants us round to the nearest hundredth, so 0, 1, 2, so 0 0.10. Okay. So roughly 10% of the population is divorced. or rather has been divorced. Keep in mind, has been divorced. I say that because I know that I've heard stats that's like saying 50% of the population has had a divorce, but there are currently 10% that are divorced right now, if these numbers are accurate. Anyways, all right. So next up, we're gonna look for a person that is female. Okay. Well, again, this chart did a pretty good job just adding all these things up for us. Well, here's the female row, right? Normally we would add all those up, but lucky for us, like I said, the textbook did it for us. So there's 131 million females that are over the age of 15, or rather 15 or older. So we would say 131 divided by, and again, the sample space here is 254. So like I said, well, let me finish this thought real fast. So like I said, our formula here, yeah, I mean, I guess it's different. I don't really don't know. There's nothing too different from this formula as opposed to the earlier one, because the numerator is still the observed number of times of our occurrence, and the denominator is still a total number of observed occurrence. So yeah, it's the exact same to me. So we've got 131 divided by 254. So I got 52, so 0.52. 0.52. So about 52% of the population is female. And I'm pretty sure that is the end of the section. Let me check real quick. One of these says, there we go. Yeah, that is the end of the section, but I will add this little bit here because I think it's pretty interesting. Alrighty, so again, we're looking at empirical probabilities. These are probabilities that we have observed. Okay, and so what's interesting here? Well, let's just read this first. Before I go over the chart. So a pattern exhibited by the empirical probabilities in the right-hand column of Table 4. As the number of tosses increases, the empirical probability tends to get closer to 0.5, which is a theoretical probability. These results give us reason to suspect that the coin is not fair. I'm sorry, give us no reason. So our table 4 illustrates an important principle when observing uncertain outcomes, such as the event of a coin landing on heads. So as an experiment is repeated more and more times, the empirical probability of an event tends to get closer to the theoretical probability of that event. This principle is known as the law of large numbers. So now I thought this was pretty interesting because when I was in grad school, we had these probability machines. They're pretty cool. You can just type some stuff in, do some coding, and you can figure out the probability of something happening. As you flip it. For this particular case, 100,000 times. You would think that if you flip it 100,000 times, that maybe it would be exactly 50-50. But as you know, I mean, the odds of something actually landing on your 100th toss, having 4,999 heads and 500,000 tails, the odds of it being a heads or tails at the end is still 50-50. So that's why we're still pretty far away. Not pretty far away, but that's why we're still not at 50-50. But for instance, let's look at the 10. All right, I've tossed a coin before, just for fun, and I know I've had heads 10 times in a row before. All right, at least 8 times. All right, but that doesn't mean that the quarter was weighted, right? That just means that, well, that was just a sample size. The closer and closer I take my number to infinity, the closer and closer it will be 50-50. And I don't know, I thought that was interesting. And now I'm sure that, yeah, that concludes today's lecture. Shoot, I did that again.